Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning. Welcome to Graph Drawing 2012. It's a great honor for me to open this conference, especially this year that the Graph Drawing Symposium celebrates its 20th anniversary. First of all, Tito and I wish to thank all people that worked hard for this event. So many thanks to Lev Nachmanson, to the other members of the organizing committee, and thanks to Microsoft for hosting this conference. We are also grateful to all the sponsors that gave to the budget a fundamental contribution. Let me thank also the program committee members who did a wonderful job in the selection of papers and posters for this conference. And special thanks go to the authors who decided to submit to GD, because their submissions represent indeed the heart of the conference. And I also want to thank the two invited speakers, so Professor Jit Bose and Professor Ben Schneiderman, for accepting our invitation. We are honored by their presence. As you know, this year, the Graph Drawing Symposium experimented for the first time in its history the double track setting for paper submissions, and we are very happy to report to you that this setting worked very well, as we received many submissions. During the business meeting, we will try to give you some statistics about submission numbers, acceptance rate, and comparisons with previous Graph Drawing editions. In the program, as you can see, each session mixes both theoretical and practical talks, and this has been done in order to have a more dynamic and lively program indeed. Near to each talk you can find a label that informs you about the corresponding track. But for these 20 years of GD, we also prepared some special initiatives. First, concerning the graph drawing contest, the usual graph drawing contest, we have this year games beside the classical competition, and we need to evaluate these games. So we warmly invite you to play with this game and to score them based on their fun factor. You will have the chance to play during coffee breaks and also during the session devoted to GD, which will take place this afternoon from 5:30 to 7 p.m. Let me thank the committee of the GD contest for this very nice initiative, and I recall you that the winners of this competition will be announced during the social dinner of tomorrow night. As a second initiative, there are two best paper awards, one for each track. We already assigned these best papers. They have been announced in the website of the conference, that also indicated in the program. But again, the winners will receive some money and certificates during the social dinner. And as a third initiative, following the suggestion of some attendees last year, we established the new award category, which we called the Best Fundamental Paper Award. The idea is to assign this award to a single paper, either a journal or a conference paper, which represents a fundamental contribution in the field of graph drawing. And hopefully this kind of award will enter in the tradition of GD and will continue next year. So, in order to assign this award, we nominated a small committee whose members are listed in the graph drawing website. And I warmly thank all these people for their support, their work on this specific task. Again, the winning paper will be announced tomorrow during the social dinner, and it will receive a special mentioning on the website of the conference for its merits in the field. I think that's all. Let me recall you that coffee breaks and lunches will take place beyond that door. There is a room there. And I wish to thank you again for attending this event. Thanks for the attention. And Tito, me, and Lev, which is not in the picture, but he's actually there, wish you a fruitful conference. Thank you very much for the attention. So probably Alex want to open the next session.
Okay, it's my pleasure to start the first session. My name is Alexander Wolff, but I'm just called Sasha, and I welcome you here too. And the first talk is by Sharir and what's your first name?
Adam Sheffer.
Adam Sheffer on counting plane graphs, cross-graph charging schemes. Please, Adam.
Okay, hi. So, as you said, I'm Adam, and I'm going to be talking about this work called Counting Plane Graphs, Cross-Graph Charging Schemes. It's a joint work with my PhD advisor, Sharir. Now, we have all sorts of results in this work, but the thing that I'm excited the most about is the technique itself, which we call cross-graph charging schemes. And I want to try to convince you that it's an interesting technique. But before I can do that, I need to present some definitions and some problems so we'll have motivation for the technique. So we're dealing with straight-edge crossing-free graphs. More specifically, we have a set of points in the plane. We're not allowed to move them. They're fixed. And we're interested in straight line segments that are not crossing. We call these plane graphs. You have some examples here. Now, notice the distinction from planar graphs. These two graphs are actually planar in the sense that if I can move the points, I can fix the problems. But in our context, they're not plane graphs. Given a set of points, for example, this set, we can embed many different such plane graphs on the set, which leads to an extremal problem. What is the maximum number of plane graphs that can be embedded over a set of endpoints? We call it PG of n. So we want to say that if you give me a set of n points, any set of n points, I can tell you that there are at most PG of n plane graphs that can be embedded over this set. We want to find out what this PG of n is. So just to make it clear, let's do an example. Let's find PG of 4, the maximum number of plane graph that can be embedded over any set of 4 points. So I need to go over all sets of 4 points in the plane. But actually, there are only two cases, a quadrilateral convex hull and a triangular one, because if I slightly perturb the points, this will not change the number of plane graphs that can be embedded over the set. So you can very easily, in 1 minute, calculate that this is what we get in both cases. And PG of 4 is 2 to the 6. Every set of 4 points to the plane that you give me, I know that there are at most 2 to the 6 plane graphs that can be embedded over it. Now, a specific type of plane graph is a triangulation. I'm sure you all know it. One definition is that it's a maximal plane graph, in the sense that I cannot add any more straight edges without crossing existing ones. And I can ask exactly the same question for triangulations. I can ask I can say TR of n is the maximal number of triangulation that can be embedded over any set of endpoints in the plane. So in a previous work, we showed that any set of endpoints in the plane has strictly less than 30 to the n triangulations that can be embedded over it. And the best known lower bound is 8.65 to the n. That is, there is a point set with this number of triangulations. So you see there's still some gap here. And there are many other variants. I can ask how many plane spanning trees can be embedded over a point set, or perfect matching, or spanning cycles. And if you look at the literature, there are works on many, many variants. There are really a lot of variants that people studied. Just in case you're curious, here are some of the best known bounds for some of these variants. So you can see that for some problems, we have there's still a large gap. For some problems, there's a slightly smaller gap. But we're still far from knowing these values. There's still a lot of work to be done here, even though there are works on these problems for over 30 years now. OK, so we have some problems. Now we can start talking about the technique. So it's called cross-graph charging schemes. So first, let's just recall what a charging scheme is. I'm sure most of you know what it is, but still, just let's do a quick reminder. So it's basically an analyzing method, a bounding method, where we put charge on vertices or edges or whatever and move it. Probably the most famous use of it is the proof of the four-color theorem, which heavily relies on a charging scheme. Now, I know you probably know what it is, but I'm going to spend 1 minute just to remind you how it works, because I'm going to need it later. So let's do a very trivial example. Let's prove this completely trivial property. A graph with n vertices and maximum degree d has an independent set of this size. For example, here I have maximum degree 3. 8 vertices, so the claim says that there's an independent set of size 2. Not very interesting. You can also find an independent set of size 3. So charging scheme is basically a double counting method. We put the charge and bound it. We move the charge and bound it again, and we have a double counting. So let's just do this very fast. So here I can put a charge of 1 on every vertex. So let's say that the charge is C, the total charge is N, right? N vertices, 1 charge on each, so this is 1 bound over the charge. Now I want to move the charge and bound it again. So each time I'm going to choose a vertex, say I choose this one, put it in my independent set and give it the entire charge of its neighbors. So for example, it will get all of the charge of these 3 vertices here, and then the graph will look like this. Now I choose another vertex, I do the same, and I'm done. No more vertices with charge. So let's use this to bound it again. Now the entire charge is on vertices of the independent set. Only on vertices of my independent set S. And each such vertex has a charge of at most d plus 1. Because, well, it started with 1 and got a charge of at most d from its neighbors. So I know that the charge is at most the number of vertices of the independent set times d plus 1. So I got 2 bounds on the charge, C equals N and this. Combining them immediately gives me the claim I wanted. Sorry for boring you with this. I just wanted to remind everyone how it works. OK. So you probably know some other charging schemes. What we do differently, what we're talking about that's different, is that we're going to move charge across different graphs. That is, a vertex in one graph might give charge to a vertex in a completely different graph. As far as I know, the first instance of such a use, an idea, was by Sharir and Wolff in 2006, where they proved that the maximum number of triangulations for any set of n points is 43 to the n. Then it wasn't really a technique. It was an analysis for a specific problem, very specific to their problem. But very soon we found out that we can use it to do other things. Here are some examples. We showed the converse, that every set of n points in the plane has at least some number of triangulations. Or we showed some properties of random triangulation. I'm going to explain what this means soon. We improved the 33 to the n down to 30 to the n. And there was even an algorithm. Razan and Wolff showed that an algorithm that gets a point set S and counts PG of S, the number of plane graphs that can be embedded over it, in a time that is exponentially faster than PG of S. That is exponentially faster than the time it will take you to enumerate all these graphs. OK, but all of these works are actually about triangulation. Even this one, the result doesn't seem like it. It's about triangulation. And the charging scheme was between vertices of different triangulations. Specifically, it relied heavily on flipping of edges in triangulation. Probably you know what it means. If not, I saw that we're going to listen to and invite a talk about this tomorrow. What we do in this work is that we show that the technique is actually much more general. It can be applied to many types of different graphs, stuff that's not related to triangulations at all. And even we found it a bit surprising, it can even be applied to some graphs that do have crossings, the non-plane, non-planar. So I'm going to show you how this works. But first, let me just show you some stuff we can do with this technique to convince you that it's interesting, that it's useful. And then I'll show you how it works. So first, we can use it to get all sorts of improved bounds. For example, we improve the upper bound of PG of n. And we get slightly better bounds for all sorts of other problems. But I don't have time to talk about them. OK, we can study random plane graphs. What's a random plane graph? So we said that if we have a point set, a random plane graph of this set is taken one uniformly chosen from the set of all plane graphs of this point set. For example, if I have this set of 3 points, there are 8 possible plane graphs. Each one is chosen with a probability of 1 over 8. These graphs are hard to study. You can't use the standard technique, the probabilistic method, or the Shreni model, etc., because you can't just take every edge with some fixed probability. You might get crossings. We're not allowed to have such crossings. So the common methods fail. And we can use cross-graph charging scheme to get properties of such graphs. Here's an example. We get all sorts of properties, just one example. Let's say that v top I is the expected number of vertices of degree I in a random plane graph. For example, if we have these 3 points again, if you go over all the possibilities, you'll see that an expectation, the number of vertices of degree 0, isolated vertices, is going to be 3/4. So we can get all sorts of bounds on the expected degrees. For example, we can show that v top 2 plus v top 3 is always at least over n over 24. That is, any point set that you take, you expect that there will be a lot of vertices of the degree 2 or 3. One of each 24 vertices in a randomly chosen graph, at least one of each 24 vertices will have a degree of 2 or 3. That's just one example. We can show all sorts of properties. And finally, I said that we can show stuff about graphs that do contain crossings, graphs that are not planar. So we study k-Quasi-Plane graphs. A k-Quasi-Plane graph can contain crossings, but it's not allowed to have a set of k pairwise crossing edges. For example, 2 quasi-plane graph does not allow to have a pair of crossing edges, so it's just a plane graph. 3 quasi-plane, this is, for example, a 3 quasi-plane. It has crossings, it's not even planar, but it doesn't have a set of 3 pairwise crossing edges. There are all sorts of works on such graphs. I think that mostly trying to bound the maximum number of edges they can have, but I'm not familiar with any previous counting results. And we show that you can upper bound the number of our technique can upper bound the number of such graphs for 3 quasi-plane graphs and 4 quasi-plane graphs. Now, you can see that these are very large bounds. This is the number of 4 quasi-plane graphs is astronomical. However, we think it's nice because it's the first time that we know that the number of such graphs is exponential. Before that, we didn't know if there might be a point set with a super exponential number of 3 or 4 quasi-plane graphs. Now we know that it cannot happen. We suspect that this is the case for every fixed k, but I'm not going to get into this. OK, so I'm going to show you how this works now, but I just want to say first, we started with a very specific, this technique started with a very specific analysis for a specific problem. Then it got generalized to a set of problems all related to triangulations. Now we show that it's even more general. It can be applied to all sorts of plane and plane-related graph types, and you can do more stuff with it. And I'm excited about this because I wonder what else we can do. Maybe we can generalize it even further, solve more problems with it. So the obvious direction is just to apply to more types of graph. I bet we can find some more types of plane-related graphs that we can use it for. But I think it's more interesting to ask what we can do beyond. For example, this technique is useful because it allows us to study a random plane graph, which is hard to study. Maybe there are different families of graphs that are hard to study in a random model, and then we can somehow use this technique to study them. Or maybe we can use it to something completely different. Why are we stuck on a specific point set? Maybe we can use it to count something like subset of subgraphs of a different family of a given graph, or I don't know what. So if you have an idea, or you might think of something that this might be applied to, I'll be very happy to talk to you. Madam, come to me at some point in the conference. Now, with the time I have left, let me just show you how this works, briefly. I'm going to show you how to bound PG of n. I'm not going to get the new improved bounds, some worse bound, just to see how this works. And first, I'm going to use this lemma. OK, first, the lemma says if I have some positive constant delta, such that this holds, we'll see what this means in a minute. V top 0 is always at least delta n. Then I get an upper bound of PG of n. Now let's do it slower and try to understand what this means. Say, for example, the delta is 1 over 100. So this says that if I can show that for any set of endpoints that I take, if I take a random graph, I expect to see at least n over 100 isolated vertices of degree 0, then I get a bound of 100 over n for the number of plane graphs. That is, if I get a lower bound on the expected number of isolated vertices in a plane graph, I get an upper bound of PG of n. I'm not going to prove it because I don't have time, but it's really not complicated to show this. I'm going to show you how to get this lower bound. And this is where the cross-graph charging scheme comes. Now we're going to move charge between vertices of different graphs, so we need a new notation. We call it a Ving. A Ving is an instance of a vertex in a graph. For example, here is a point set. Here's some vertex V. Here's a graph over this point set G. And a Ving is an instance of V in G. It's specifically, you can think of it as a pair of a vertex and a graph. And if the vertex has a degree of I in the graph, we call it an I-Ving. For example, this is a 4-Ving because V has a degree of 4. OK, so let's use the charging scheme. We want to put charge and bound the charge, and then move the charge and bound it again. Double counting, just as we did before. So we're going to put a charge of 7 minus I for every Ving in every graph. For example, here is a 5-Ving, got a charge of 2. 1-Ving got a charge of 6. A graph with a Ving with a very large degree will have a very negative charge. This is very similar to what happens in the proof of the four-color theorem, where they give every vertex a charge of 6 minus I. And we use also a very similar analysis that shows you that on average, not on average, the total charge is larger than the total number of Vings. Okay, it's not hard to show. It's very much like what's happening on the proof of the four-color theorem. That's one bound of the charge. on the charge. The charge is larger than the number of wings. Now we want to move the charge and bound it in a different way. So we're going to move the entire charge to 0 wings. Just like before we moved the entire charge to vertices of the independent set, now we're going to move it to 0 wings. Let's take this 3 wing. It has a charge of 4. It's in the graph G. Now we want to throw away all the edges that are adjacent to it. All these 3 edges, we get a different graph G prime. In this graph, our vertex is a 0 wing because there are no edges adjacent to it. So this 3 wing is going to give all of its charge to this 0 wing. And that's going to happen for all of the wings. Every wing is going to give its charge to a 0 wing by throwing all of the edges that are adjacent to it. If you do this, you can show that every 0 wing is charged at most 2 to the 12. This may seem counterintuitive because what if some 0 wing is charged by 1 million 1 wings? Each 1 wing has a charge of 6. So this is a charge of 6 million. It's much larger. But the intuition is that if there are a lot of wings with a positive charge that charge your 0 wings, there will be a lot of wings with a negative charge that charge it. For example, if you have 1 million 1 wings that charge it, you're going to expect to find more than 1 million 100 wings that charge it. And each one of them has a charge of minus 93. So if there are a lot of wings that charge it, it's going to have a very negative charge. This bound, 2 to the 12, it's tight, and it's obtained when there are, I think, 12 1 wings that charge it. OK, so let me just wrap it up. So we counted the charge in 2 ways. First, we said that the total charge is larger than the total number of wings. Then we moved the entire charge and said that the total charge is at most the number of 0 wings times 2 to the 12, because all the charge is now in 0 wings. Combining these two gives us exactly what we want, the lower bound and the expected number of 0 wings in a graph. So this will give us a rather bad bound. It will give us a bound of 2 to the 12n. But using some more tricks, you get the new improved bound that I mentioned before. And that's it. Thank you very much.
Other questions for Adam? Very clear presentation. Thank you.
Thank you.
Nice talk. The next speaker is Joe Fowler, who will talk about planar preprocessing for string embedders, which is joint work with Studi.
My name is Joe Fowler. I'm from the University of Arizona. This work is in conjunction with Stefan Kobourov, and I'll be talking about planar preprocessing for string embedders. So string embedders are nice drawing algorithms that can draw any graph, not necessarily just planar graphs, of course. And they work by, there's different classes. There's like Frutman and Reingold, which are force-directed algorithms. There's also like multi-dimensional scaling ones by Kamada and Clay. But the idea, like with the FR one, is that nodes that are adjacent are pulled toward each other. Nodes that are non-adjacent are pushed from each other. They iterate so many times, and they tend to give fairly decent graph aesthetics, like in terms of node separation, edge length ratios, trying to avoid small edges versus big edges, angular resolution, trying to avoid having the really sharp angles. But they don't consider edge crossing, straight line
Insist for the recording.
Okay. Do I need to repeat myself, or did I get that? Okay. Continuing. So with planar drawing algorithms, of course, you get rid of all the crossings, and they run much faster. They run in linear time compared to string embedders that can take quite a bit longer, like quadratic time per iteration or more. But one of the drawbacks of straight line planar algorithms like for Sapak and Pollock, Schneider, Kant, is that they tend to have areas where they'll really compact all the nodes into a small place, which will lead to small edges compared to long edges. And they don't do the best job with angular resolution either. So the question that we're asking here is that, well, string embedders are influenced by the initial layout you start off with. So typically they start off with a random layout, and they iterate from there. Now, you would think that if you give it a planar layout where it starts off with planar, it would do better crossing-wise than with the random one that tends to have a lot of crossings. But that isn't necessarily obvious, because these algorithms, by the very nature of how they work, they tend to do these really big initial moves in the beginning, and they totally destroy the planarity. So it would be nice, because crossings do tend to interfere with the readability of a graph, if we could do something to help reduce the crossings generated by these spring embedders, because they do well otherwise. Now, in terms of previous work, there has been some, like Harrell and Sardis, use like simulated annealing, and they're a fairly caustic algorithm using, but they improved upon a planar layout. Berthold actually devised one that took edges and vertices into account, but then had to consider all the edge and vertex pairs. In comparing like multidimensional scaling to force-directed layouts, Brandis and Pick showed that they are indeed better at giving your ideal edge lengths. So one application for when you might want to like lay out a planar graph using a force-directed method is by Von Hamm and Wattenberg. Now what they did is they had a real-world graph, was a nice one where it was a lot of clusters, but it had small diameter. So it had some edges that were common to many shortest paths. And so when you use your typical force-directed algorithm to lay this thing out, it just looked like a hairball. So their idea was to extract a planar subgraph with the lowest betweenness, which is the betweenness based off the number of shortest paths an edge is in. And they got about 80% of the edges were in this planar subgraph, and they used the force-direct algorithm to lay it out, and then add in the height between edges later. And that was a much more readable graph. So this is an explicit example where you might want to use force-directed on planar subgraphs. One thing that's sort of related to what we did is Didimo, Lida, and Romeo used polyline layouts where you have an orthogonal layout or one from planarization, and they iterate on that, and they had their own force-directed layout that didn't introduce crossing, to actually reduce it, but it had curves or bends in the edges, which is different from what we're talking about. I'm talking about straight line drawings. Now, in our experiments, we had 6 different libraries that we examined. 2 of them were trees. The proof for one is uniformly sampled labeled trees, where then we discard the label. That's not the same thing as unlabeled. And random trees, which is the standard one where you just randomly attach edges. So those are trees, 2 different types. Fussy graphs are uniformly sampled unlabeled planar graphs, not plane, but planar graphs. And expansion graphs are random tri-connected graphs formed by starting off with a K4 and randomly uncontracting a vertex into 2 vertices and then distributing the adjacencies to keep it tri-connected. We also looked at 2 real-world graph sets, Rome graphs and 18 graphs, and picked the ones that were planar from that. So out of the Rome library, there's over 11,000, 3,200 were still planar. Now, for the generated sets, the first 4 ones, we went from n equals 10 to the n is the number of vertices, to 100, and we had 10 each. And you'll see that with trees, of course, the 50 is the median. You have, your average degree is about 2. And when you go from, like, for the truly random ones, fussy, go from 2.2 to 4.79, a range. But still, it's generally twice as many edges as a tree. And expansion graphs are a little bit more. But these real-world graphs, which is interesting, their median values in terms of the average degree is fairly close to trees. So there are not that many more edges than trees. So it shows that people typically tend to lay out these sparse graphs, and oftentimes they can be planar. So in terms of our experiment, what we did was that, of course, we have our initial random layout that most of them start off with. And then we looked at 3 different planar drawing algorithms. We used OGDF for everything, which is Open Graph Drawing Framework that used to be AGD. And FAP is the classic one for say, Pack and Pollock on the 2n-4 by n-2 grid using canonical ordering. Schneider uses a different method with the Schneider realizer. Gets it more compact on n-2 by n-2 grid, actually half of that, so it's most compact. Kant is more like FPP, but has a better choice for outer face and whatnot, so it tends to not compact things quite as much. Now, for the spring embedders, we mainly look at the Frutman and Rheingold versus Kaman and Quay. We also, this was another simple one, just we threw in but it's not really, it's meant more as a pre-processing step itself. Now, there's two different versions of this FR algorithm in OGDF. There is the standard one, which is actually a grid variant approximation. Then they have one that also does exact computation that takes longer to run, of course. And we're mainly trying to compare the FR variance to KK, the Kamana and Quay multidimensional scaling. Now, we looked at 4 different aesthetics. Number of crossings, just simple number. These other ones are a little bit more involved. So minimum angle metric, this is taken from Helen Perch's article about different metrics for graphs. And here you are taking the ideal angle. So if you have 4 edges incident to angle, the ideal angle that you can put it in where everything's nicely distributed is 90 degrees. And if you have 100, then it would be, or 180 would just be 1 degree. So you're not going to penalize a sharp degree just because it's a high degree vertex. And you're taking the average deviation of this, subtracting it from 1. So 0 is bad, 1 is good. So 1 is when you have perpendicular angular resolution. 0 is when everything's just on top of each other. And these other ones work similar way with edge lengths. This is fairly straightforward, doing a similar thing with edge lengths. The only little difference is doing this little bit here so that it always keeps it between 0 and 1, either subtracting or dividing it by the average or the maximum minus average. Now, node separation is sort of the least standard out of all these, where here we use the concept of separating rectangles. So the idea is that I have a node, and I try to find the largest rectangle that contains the node inside the bounding box that contains all the nodes, that doesn't contain any other node. So rather than just looking at the node that's nearest to it, you're looking at this bounding rectangle because 2 nodes might be next to each other but may have a lot of space to either side. So this tries to take into account for that. Now, here are some sample layouts that we get for all this. This is for a graph with 55 nodes, 121 edges from the expansion library. Now, the first column is just the different initial placements. Random, as you can see, is quite bad with almost 1,600 crossings. And of course, you get no crossings here, but the other metrics are, especially edge and node separation, are worse than they are with a random one. As you can see, like here, there's really compacted areas where a lot of the graph is drawn. Now, with the Freiman-Reingold, the first one is the approximation, the next one is the exact. And you see they're somewhat similar structure, but not quite the same. But generally, you have fewer crossings with the exact one. Kamana and Quay, just different layouts. And what we found in general, this is not really affected by the initial layout. And we have a sort of similar thing going on with stress majorization. Now, in terms of the aesthetics of just the placers all by themselves without doing anything else, we see that, of course, the random one is the dark line where you get a quadratic number of crossings based off the number of nodes. And you have far more crossings than you do with the planar layouts, which are 0. Now, with minimum angle, the minimum angle is actually worse with the random one than it is with the planar ones. So it's not quite as bad. But the planar ones are worse than just a pure really random layout, which doesn't look all that great for both edge lengths and node separation. And we see the same thing with the other set of the 3 graphs in the library. Now, when we look at the base embedder aesthetics, this is using the random placement. This is what's typically done. We see several things. Okay, so the dark green line here is the FR with the approximate. The dashed one that's also green is the exact one. This purple one here that sometimes is dashed but sometimes looks solid is stress majorization. And the orange one is KK. Now, in general, like especially with trees, Kamana and Quay gets rid of virtually all the crossings. And it does fewer crossings with the denser graphs and also with the real world graphs. And with the other aesthetics, it also has, and generally it's always the best, except for this one case where the approximate version of FR is a little bit better with the node separation for your purely random planar graph. And the other three are similar. Now, so for our results, this is a somewhat different layout. See, before this one is with the absolute values, and this one is with percent improvement. Okay, so here we're talking about what is the percentage of improvement or worsening. So for the first column, we see a lot of improvement in terms of crossings. So for both the FR ones, we're getting rid of a lot of crossings with the trees. In some cases, for the between 20 to 40, virtually eliminating all the crossings, and then getting rid of most of them otherwise. We get about a 20 to 40% improvement otherwise. Also, even stress majorization gets rid of quite a bit, even though it doesn't look all that great. This is final result, but KK is not really affected. It's, for the most part, whatever variation you see is mostly noise. Now, the good thing that we see is that our other aesthetics are not really adversely impacted. For the most part, they stay the same. That we're not really worsening, and sometimes in some cases we're actually improving the minimum angle a bit, which is interesting. But for the edge lengths and the node separation, for the most part, they remain the same with some noise. So FPP, which is, so CANT is an improved version of FPP. FPP doesn't do quite as good as CANT. And so we see that even depending on what planar drawing you put in, you get, that can affect the layout. So it's even sensitive between these two. Because if you look, so this is proof for here, you get a lot of crossing elimination initially with CANT immediately, whereas here, not so much. And it doesn't get up to 100 with FPP. And Schneider has similar results to these. So that's interesting. So in terms of what we found was, well, when we're actually just comparing raw aesthetics, so KK isn't really affected, but Kobourov is an expensive algorithm. It takes a while to run. And in our case, if we're doing the exact version of FRE plus this very cheap pre-processing step, oftentimes that would run 20 times faster for larger graphs in our set. And so the question then becomes is, well, how do these two just compare in this raw comparison? And you see that in terms of crossings, they do very, very similar. Now, this first graph might look worse than it really is, but it's just going up to 4. So, I mean, it's getting rid of most of the crossings in trees. So it's very comparable in terms of crossings for these graphs where CANT and FRE have a slight advantage over KK for the denser graphs. It's only worse with the trees. The minimum angle, for the most part, is just slightly better with trees, and for the most part the same for the other two. Now, for edge lengths and node separation, then in this case, KK is better. It's better across the board. So it's consistently at 0.8, whereas other ones go down to 0.6. But still, this is a more expensive algorithm to run KK, and this is a much cheaper algorithm to run. So we get similar results with this pre-processing as you does with this other more expensive one. So in terms of our conclusions, we have several. We see that we can do this linear pre-processing step that doesn't really add much to the time. And it does have an effect upon the crossings, at least for the Feynman and Rutter ones. So for sparser graphs, it does quite a bit better. But even for denser graphs, we see an improvement, which is key. And the most important thing is that the other aesthetics, for the most part, are not adversely affected. So you're not doing this trade-off that you're doing initially with spring embedders where you're trading planarity for readability as much. So we also noticed that the multidimensional scaling is relatively unaffected by planar preprocessing, which makes sense given how it works by throwing everything up into a high dimensional space and then projecting it down. And we saw, as I was showing, that CANT and FRE is competitive with KK, which gives some motivation for doing this. Now, in terms of future work, we have several things that we can do. So one of the things, of course, is see, when we did this with OGDF, we just used it out of the box. We did not do any messing around with parameters or anything. So we could try to adjust the ideal edge length with what you actually get as the average edge length, which might help some. And an important thing with FR is I said it can do these big initial moves. And if we can adjust the cooling schedule so that it tries to avoid doing these big moves to the extent that's going to introduce a lot of crossings, that would be good. We also really only went up to 100 nodes. These are still relatively small graphs. And it'd be interesting to see, do these results continue for very large n? If you go to 1,000 or 10,000, do you continue to see this kind of improvement, or is it just initial? But I think even a more interesting thing to do is that, well, planar graphs are there sometimes, but as in the case for Rome, they're only like 1/3 of the time for those. So we would like to be able to process to non-planar graphs. So we could extract a planar subgraph and draw that first and see if that helps. Now, if we're drawing the planar subgraph and just drawing that, then you throw in the other edges, that can adversely affect those other aesthetics. And also, we just looked at these other aesthetics in terms of edge length, node separation, and angular resolution. But there's other ones like asymmetry and there's many other sites that escape me at this moment. So, and I think one last other thing of future work, and that'll be the end of my talk, is that we can maybe try to work with trying to get a smarter force-directed algorithm, kind of using the technique used with Didimo and them, and try to get it so that we get one that doesn't introduce crossings as much, and see how that works as well. Okay, so thank you.
Any questions for Joe?
So when you apply a planar drawing algorithm, what planar embedding do you use?
A planar embedding?
Which one? So especially for the Roman 18th.
Yeah, we use the default one with OGF where it augments it to a biconnected graph, and then picks one for a random one from that.
There are also algorithms where you, for example, compute a maximal external phase or something like that. Maybe that would be helpful.
Yeah. We just used, and in each case we just used the default, so we did not look at trying to pick better embeddings. And also to make one note, in terms of our experiments, we ran each graph 10 times with 10 different random embeddings. So we didn't just pick one, we tried 10 different ones, but we didn't do anything special about picking those 10.
Okay. I have a similar question. This FPP, for example, assumes that the input is triangulated.
Yes.
So you have to extend your graph.
Oh yeah, exactly. Yeah, and
you can do it in different ways. So did you try that?
No, we did.
Of course, lots of effects.
Yeah, exactly. So that's one reason why.
And what is the effect?
Well, I think
what is better than what? How would you do that?
Well, I would think that with Kant, it does a better job. It does a better job of augmenting the graph initially.
Yeah, because it's not. It doesn't. It's not fully triangulated.
Yeah. And so that, but yeah, just to the point of getting it to the point where you can even use Kant, there's a lot of different choices you can make there. So certainly, augmenting the graph would definitely help. Okay. Oh, yeah.
One more question.
This paper is very empirical, and you may found some results about reducing crossings with force-directed methods. Is there any theorem to prove?
Not at this point, not off the top of my head.
You don't know what theorem you would try to prove.
What?
You don't even know.
Oh no! Well, I'm trying to. I mean, basically, the idea is that spring embedders are affected. The input is affected by the number of crossings. Yeah. So in that way, we're empirically trying to show that.
You think you could formulate it as a theorem and prove it?
Possibly, if you really understood how. If you had to really restrict the problem, but yeah, possibly. A good idea.
Okay, thanks again, Joe. And the next talk is by Thomas Blasius about disconnectivity and relative positions in simultaneous embeddings. And this is joint work with Eades in the audience.
Okay, thank you.
As mentioned, this is joint work with Eades, and it's about simultaneous embedding with fixed edges where the graph is not necessarily connected. Okay, I want to start with definition of the problem. We have two graphs as input, having a common subgraph, and we want to find planar drawings of each of the graph such that they induce the same drawing on the common graph. So in this example, we have this red graph and the blue and the green graph, and both are planar. And here on the right, we have a simultaneous embedding with fixed edges, where in particular, for example, this edge here, which is a common edge, is drawn the same in both drawings. And each of the drawing is planar, but we are allowed to have crossings between red and green edges. Okay, there's a nice theorem by Nguyen and Schultz stating that we do not need to care about the real drawing, but can deal with the embedding only. Or more precisely, these two graphs, G1 and G2, have a simultaneous embedding with fixed edges if and only if they admit planar embeddings that induce the same planar embedding on the common graph. Now, what does it mean to induce the same planar embedding? There we have to look at what embedding really means. And embedding consists of two parts. First, we need a consistent order of edges around vertices, and the relative positions of connected components to each other need to be also consistent. So previous results mostly ignore the right part with the relative positions completely and only deal with the ordering of edges around vertices by either assuming that the common graph is connected or that it's a forest. There's one result that's somehow in between, at least a little bit, namely the case where the common graph has one cycle, and then you have to also decide whether to put other connected components into the cycle or outside of the cycle. We do the opposite to these approaches by ignoring the orders of edges around vertices and only looking at relative positions of connected components to each other. And this is done by assuming that the common graph consists of disjoint cycles. And we will see that this can be solved in linear time. Okay, I want to start with an overview. First of all, we need some kind of representation of the planar embeddings of a set of cycles. And to this end, we just orient the cycles arbitrarily and then use pairwise relative positions to describe the embedding. So in this example, we have the blue and the red graph cycle on the same side, namely on the left side of the green cycle. So here these two relative positions are left. Or another example, the red cycle is on the right of the blue cycle, so the relative position of the red cycle with respect to the blue cycle is right. If we have an assignment of left and right values to these relative positions, then we call this a semi-embedding of the cycles. And of course, not every semi-embedding is also an embedding of the cycles, because we can, for example, not just put the red cycle to the right, so inside of the green cycle, without changing any other relative positions. Okay, what we then do is we do not consider two graphs having the set of cycles as common graph, but we look at a single graph, a single connected graph containing this set of cycles. And then we show that there's a data structure, which we call the constraint cycle tree, or CC tree for short, that represents all the semi-embeddings of the set of cycles that can be induced by an embedding of the graph G. We further show that the intersection of two CC trees is again a CC tree. And this essentially solves simultaneous embedding with fixed edges for this case, because we just take the CC tree of the first graph representing the embeddings of the cycles with respect to the first graph, and the second CC tree representing the embeddings of the cycles that can be induced by the second graph, and then we check whether the intersection is empty or not. Okay, so let's start with the graph, which is connected and that contains a set of disjoint cycles. Now, what are the embedding choices? For example, we can reorder parallel subgraphs. So in this case, we change the order of the green path with this larger component. And this changes the relative position of these two cycles with respect to the green cycle. And the nice thing is that this is the only possibility to change these relative positions. So we get that this equation up there always holds, namely that the red cycle and the blue cycle are always on the same side of the green cycle. Another way to change the embedding is flipping tri-connected components. So in this case, this component was flipped. And this, of course, changes the orientation of the blue and the red cycle, so of all cycles in this tri-connected component. And thus, it also changes the relative positions of all other cycles with respect to these cycles. And again, this is the only way to change these relative positions. So we get these constraints there, namely that if we look at the blue cycle, then the orange and the green one are on the same side, and the red is on the opposite side. And similar for the red cycle, all other cycles are on the same side, no matter which embedding we choose for the graph G. And then we can also change the embedding around cut vertices, and this may also yield some additional constraints which are similar to that. And what we can show is that these constraints are not only sufficient but also necessary, which means the following. So the necessity means that if we choose an embedding of the graph G and look at the embedding of the cycles, the resulting embedding of the cycles, then this semi-embedding satisfies these conditions. And the other way around, if we take a semi-embedding satisfying these conditions, then we also find an embedding of the graph G that induces this embedding on the cycles. Okay, this essentially yields already a solution of the simultaneous embedding with fixed edges problem, because we have a bijection between an instance of two satisfiability and all embeddings of the cycles that can be induced by a connected graph. So this instance of two satisfiability is just because we have a set of equations and inequalities between binary variables that can take the values left or right. The problem is that we have a quadratic number of variables because we consider pairwise relative positions as variables. And the solution to that is the CC tree, the constraint cycle tree, which I want to introduce now. Here again are the constraints we need to satisfy. And to construct the constraint cycle tree, we start with the original graph and take a minimal connected subgraph containing all the cycles. So in this case, we just remove these gray edges here. Then we replace paths with single edges. So this path of length 2 is replaced by this edge. And now we essentially have a tree structure. We have this orange cycle connected to the green cycle, which is connected to the blue cycle, and this is connected to the red cycle. And if you contract the cycles to single nodes, then we get, in this case, a path, or in general, a tree. We then use this tree, or each half edge in this tree, to represent one decision. So I just make an example. If we consider this half edge here, or this edge connected to the green cycle, then this represents the decision of putting the adjacent vertex either to the left or to the right of this cycle. And we additionally say that the tree structure enforces that the whole subtree that is connected over this edge is also put on the same side of this cycle. Another example would be the decision made here. There we decide to put the blue cycle either to the left or to the right of the red cycle, and all other cycles have to follow because of the tree structure, because this whole subtree is connected over this edge. And then what we do then is we take the constraints we have up there, and somehow apply them to these decisions we can make in the tree. So, for example, the first constraint up there states that the relative position we choose here is the same as the relative position of C3 with respect to C1, but there's no edge. So we just throw away this constraint. And the nice thing is that, at least in this case, the tree structure automatically enforces that this and this cycle are on the same side of C1. Similar, we don't have an edge between C4 and C2, so we throw away this first equation. But for this inequality, we have we get that the decision we make here and the decision we make here need to be the opposite. And what we can show is that the resulting tree and the set of embeddings that are represented by this resulting tree are exactly the embeddings of the cycles that can be induced by an embedding of the graph. This means in particular that we didn't throw away too many of the constraints we have, and that the tree structure did not enforce too many constraints that are not necessary. Okay, so let's state this theorem once again, and we get another theorem, namely that we can compute this constraint cycle tree in linear time. Moreover, the intersection, as mentioned before, of two constraint cycle trees is again a constraint cycle tree, and it can be computed in linear time. And this directly yields that if we have two connected graphs, G1 and G2, with intersection graph is a set of disjoint cycles, then we can test in linear time whether G1 and G2 have a simultaneous embedding with fixed edges by just taking the constraint cycle tree with respect to G1 and the constraint cycle tree with respect to G2, and intersect those. Just one word to this thing here. So you can probably imagine if the underlying tree structure of these two constraint cycle trees we have is the same, then this is pretty simple. We just take the union of all constraints we have on this tree. But if we have two different tree structures, then we need to do something more. We need to transform somehow this tree structure from one tree into the other tree. But this is possible in every case. Okay, so now we have this restriction there that the graph G1 and G2 are connected, and we wanted to deal with disconnectivity. So we need to deal with that somehow. And the bad news is that the CC trees don't work for this case. But we get a more general result, namely that if we have an instance of simultaneous embedding with fixed edges, then we can always construct an equivalent instance in linear time such that both graphs are connected. And this does not only apply for the case where the common graph is a set of disjoint cycles, but for all instances of simultaneous embedding with fixed edges. Now, of course, the CC trees can also be used to solve the problem for more than two graphs if they all intersect in the same common graph consisting of a set of pairwise disjoint cycles, because we can just intersect an arbitrary number of CC trees. And we can extend the result to the case where the common graph consists of a set of connected components, each with a fixed planar embedding. In this case, we have the problem that the decisions we make, the relative positions, are not binary choices, because we don't have just left and right, but we have phases we have to decide where to put the other components in. And in this case, we need quadratic time. Okay, so I want to conclude with a slide I had before and with an open question, which is, in our opinion, one of the main open questions for simultaneous embedding with fixed edges, namely, can we deal with both of the parts consisting that are contained in a choice of an embedding at the same time? So can we, at the same time, enforce consistency of relative positions and ordering of edges around vertices? Okay, thank you.
Questions for Thomas? Okay, thanks again. Okay, the next talk is given by Nguyen. I'm sorry for my pronunciation. The title is Stream-ED, Stream Edge Bundling. And it's joint work of Peter Eades and Soki.
Good morning, everyone. Thank you, Alex, for introducing me. My name is Nguyen. So before the talk, I want to mention about the big data. Recently, big data is something real, and big data analytics is something real demand that people need in the industry. And the four challenges with big data is that we have the volume, the velocity, and the variety, and also the veracity. And today I'm going to talk, my talk is focused on the first three, the volume, velocity, and the variety. And for the veracity or the truthfulness, or reliability, Peter will going to talk in the poster session. So this is the outline of my talk. So basically, data stream is ubiquitous. It's everywhere, and graph stream is becoming popular. So now, before the talk, we need to distinguish between dynamic graph visualization and stream graph visualization. So for dynamic graph visualization, existing methods, we focus on a quite limited number of static graphs. And for example, individual graphs, you can see G1, G2, G3. Each of them can be aggregate data from yearly report or monthly report. And for stream graph visualization, we focus more on like the data is very long dimension, can be the size big. But for this work, we only focus on the time dimension is very long. And the big data that we do in financial activities and flight monitoring activities, it can be millions of records, and it can be stored in gigabytes. So the real motivation for our work is that one. And the challenges for stream graph visualization is we want to be able to see the trends and change over time. And also we want to see to make a preservation of mental map so that the user can see what's going on. And recent survey by Randes, the control between breathability and stability. But for this work, we focus more on the visual cluster. For node-link diagram, no matter what methods we going to use, we have to solve the visual cluster problems. So this is the motivation of our work. And edge bundling, I think, is one of the recent popular topic in InfoVis community and graph growing community. And there's a few representative work. Before going into details about our research, I want to show you some movie. So here I'm going to show you two types of animation, events by animations. One is with the static layout, that and the other one with the dynamic layout. This is the simulation of the hijacking activities on the 11 years ago. And for it not representing the city, and the edges representing the flight connecting between the airport. And the color representing whether the flight is red mean early and green mean delay. And then so the hijacking activities happen around from 8 a.m. to 9. Then you can see after the first attack, the number of flights significantly dropped. And you can also see the distribution around US. This is after the second attack. Oh, okay, so here again. So about 9:20, it's almost shut down. No more flight, and it happened for more than half a day, and then it resumed almost at midnight. And then the next day, there's no flight. I think one single flight. And for the second animation, I want to show you how our bundling framework can work for dynamic layout. And for this one, I use the circular layout as a start point. And each node is a trader, and the connection is the trades between them. And you can see the animation over time from the market start. So when a trade happens, the active trader comes toward the center, and the bundling based on our aggregate compatibility that I'm going to introduce you later. Yep. So now come back to so you already have some rough idea about what I'm doing. So now I'm going to talk in details about what is stream edge bundling. We introduced the stream EB framework, and also we introduced two types of new compatibilities for stream edges, and also we have introduced two types of stream bundling methods. And the motivation is that we want to analyze the big data, the massive relational time series in financial activities and flight monitoring activities. So first of all, I want to introduce the bundling pipeline. And stream EB is the core of the pipeline. It would be here. And the important point I want to make is our pipeline can handle dynamic, like from the routing result, we can have the mapping again that not previously studied before. Now, so what is stream actually? In our model, we study a stream as a continuous flow of stream wraps, stream elements, and window processing is one of the popular techniques in data mining for mining wrap streams. And in our study, we studied two ways for window processing: is sequence-based and time-based. And for each element, the most general form is a node connect to a node at a given timestamp with duration. The duration is important for some application, but maybe not so for the other application. For example, like for flight monitoring system, duration is something important because we need to know when it's going to depart and landing, so that we can reserve some facilities. But for some other application like stop, a trace is a trace, and normally we don't want to reverse the trace that already happened, unless some case that you make some illegal trace and then they have to cancel, but it's really rare. But in general, our model can handle those. We introduce there are four types of compatibility metrics. The first one is temporal compatibility. The basic idea is that for each stream edge, we have the start time and the end time happening some duration di, and we define several metrics to compute the compatibility between them. It can be based on the timestamp, the duration, the end time, the time overlapping. The idea is that we want to group related stream edges together so that we can do some analysis on that. For neighborhood compatibility, we also want to study some causal relation between the edges. and data-driven capabilities. It's kind of like we have the multiple dimensional data, and we want to group similar edges together based on the semantic, the multiple dimensional vectors. For aggregate, the final capabilities, we aggregate the 4 capabilities, the temporal capability, neighborhood, data-driven, and spatial capability together, and we start building our bundling methods based on this aggregate capability. We introduced 2 methods, force-directed and tree-based at bundling. The first one is force-directed string bundling with dynamic layout. We extend the classic string algorithm. We introduce a new type of force, the bundle-aware force. Previously, we only have the string force and repulsive force and some external force. Now we introduce the bundle-aware force, and the idea is that the bundle results can help us to make the layout nicer in terms of the bundles. And the simple version is simply extend the force-directed at bundling methods of Horton, and the idea is we integrate the new aggregate capability method into this. We also introduce some optimization in case we want to bundle data, but the nodes had fixed locations, and we want to save a lot of computations, and we introduce something like a 2-step process, the offline and the online. For the offline step, we do some recomputation of the compatibility and the compatible edges, and then on the online step, we just reuse the information that we already computed, and then we save the running times. The fourth method is tree-based bundling. We introduce a double interpolation process. You can read our paper and then see. For implementation, we implemented on geometry framework, and also I do it with Neo4j graph database. The motivation is we want to analyze big graphs. And here's some result that you can see. So we can compare from 8 a.m., 8:30, 9 a.m., and 9:20, and the effects of the hijacking activities on the flights in the US on the date. And you can see that from 8 to 8:30, there's a significant drop of number of flights, and going on like before the certain time, it dropped even more. And this is how the result look like using our tree-based bundling. It's nice, but somehow like it may introduce some artifacts due to sort of like rerouting almost like near the tree structures hierarchy. And this is how how our framework can produce result for trading activities. The node representing traders, and the edge is representing the connecting between them. And this is using force-directed at bundling, same layout, and the layout using multiple dimensional scaling based on the trading, the frequency of the stock trades between the traders. And this is circular, how it look like using tree-based. And this is circular using force-directed with fog-directed layout as well. That you can see in the animation. For performance, from what we study, it seems that 3x bundling is the fastest one because it saves a lot of without doing many iterations. And also for our optimization method, it also can reduce the computation cost. But in general, we need to do it more to make it really real time. For limitations, future work. Our method is currently it provides the flexibility capability, and but it also requires the user involved to adjust the bundling parameters. And currently, the number of parameters is not small, and how to make the adjustment is based on the experience to play with the tools, and also what really they need to see. And for future work, we plan to interact with some semantic zooms, and also we want to adopt some faster and more scalable methods so that we can adapt to make analyze bigger graphs. And also we want to analyze hierarchical data, for example, in software data. Yeah, that's the end of my talk. Thank you very much.
Thank you. Other questions for Nguyen? No questions? Thanks again.
Thank you.